Hello friends, welcome to this lecture series on cosmological perturbation theory. In the standard model of cosmology, we have seen the universe which is homogeneous and isotropic. Now we will move away from homogeneity and isotropy and talk about the universe which is perturbed. Let us now look at some notation that we are going to use in this lecture series. We have a universe which is filled with cosmological fields such as the density field, the energy momentum tensor field, the temperature field. In the first part of the course, we will be developing a framework to study the perturbations in these cosmological fields. Before we come to the specific fields like the density field, the energy momentum tensor or the temperature field, we want to develop a framework using some generic notation in which I will be referring to some arbitrary fields. So first of all, let us develop the framework that we require to study the perturbed cosmological fields using some generic notation. In the notation that I will be using for developing the framework, I will use this big curly F to refer to any arbitrary field that could be a scalar, a vector, or a tensor. So when I am using this big curly F, this means that I am referring to field which could be of any type. It could be scalar, it could be vector, or it could be tensor. And the examples are all the examples which I have mentioned here. For example, if I am saying density, pressure, which are scalar fields, velocity, which is a vector field, G alpha beta, T alpha beta, these are all tensor fields, and they all come under this big curly F. Big curly F is any arbitrary field that could be a scalar, a vector, or a tensor of any type. Then if I am using small f, that means I am referring to an arbitrary scalar field. Examples are density and pressure. And if I am using f alpha, that means I am referring to an arbitrary vector field. Example is the velocity of the fluid. If I am using this notation f alpha beta, this is an arbitrary tensor of type 0, 2. Examples are G alpha beta, T alpha beta. And if I am using this notation, that means I am referring to tensor of type 1, 1. For example, this T alpha beta. If I am using this notation, that means I am referring to tensor of type 2, 0. For example, T alpha beta. Now we have seen that in the homogeneous and isotropic universe, the fields at a given point of time are the value of any field at a given point of time is the same everywhere. So the field in homogeneous and isotropic universe is not a function of its location in the universe, but it is a function of time only. So in the homogeneous universe, if I am using this notation curly f for arbitrary field, then I will write this curly f is a function of this arbitrary field is a function of time only, and this t is cosmic time and eta is the conformal time. So it is a function of time only. Then in homogeneous and anisotropic universe, so the real universe, which is not homogeneous, which is not isotropic, there will be spatial dependence also. So a field, a generic field, curly f, depends not just on time, but also on the location in the universe. So there is spatial dependence also. And the real universe is the inhomogeneous and anisotropic universe. So this is the real universe, inhomogeneous and anisotropic. And this homogeneous and isotropic that we studied in the standard model of cosmology is an ideal picture, is an approximated picture of the universe which is real, which is inhomogeneous and anisotropic. Thanks for watching.